just saying thank you very much for the organizers, because I've been a fan of ACVR, because I do believe that you keep the light of asking the tough questions when it comes to making sure that perception links to action, and that we ask also how to make sure that these systems work with people. And this is indeed what my talk is about, which is about augmenting people. And I will be talking specifically about two of my academic works that are related to this aspect. Myself, I've been, as Antonino, thank you for the introduction, has mentioned, I have been extremely interested through my career in trying to understand what is the best way in which we can provide the right information to the user with the right context from artificial systems in order to be more efficient. And the two parts that I would like to concentrate my talk today is about cognitive assistance for augmented and mixed reality systems, and also a new type of robotic devices that we have developed in my group that we call handheld robotics. And just to start with the first part, this is something that goes back to my early days when I started working towards my PhD on how to build early augmented reality systems. And what it actually matters when it comes to this. And the work I will present is in collaboration with my students, Tisid and Hazel, and also my colleague, Dima Damen, all of them from Bristol University. But let me take one long step back and try to look at how the future seemed to look 30 years ago. So what you see here is, in my opinion, one of the key milestones. There have been many milestones along the way of augmented and mixed reality systems, but this is the system developed by my colleagues at Columbia University, Steve Feiner and his team, the Karma system. You might have come across this before. Let me just, for the benefit of those who haven't, explain what is happening here. So what you see here is a display that is positioned based on these triangular markers that you may be able to see here, that allow everything, using ultrasonic systems, allows everything to be positioned in 6D. So when you know where everything is, you can project the right information according to the perspective of the person that is looking at this scene. So this is how a typical augmented reality system looked back then, and in many respects is still aiming to look nowadays. But as part of my PhD, which is now 20 years ago, I worked on some of the very early, many consider the very first visual Islam system, together with Andy Davison and David Murray at Oxford, that used visual Islam to perform augmented reality in a small room, in a small environment. And so what you see here, let me just pause this and try to make sure that I optimize this for video. But what you see here is a system that is moving through space and is estimating the position of the camera, which in this case is actually a wearable camera that is here, that is meant to be an interface between a remote expert and a local person. So since then, I was very keen on trying to make sure there was always a human or humans in the loop. And this is back in 2003. So some of the augmentations that we were able to make in real time, because all this is working in real time, 30 frames per second, are very basic. So in this case, it's just these yellow cubes in 3D that the remote operator is able to drop into the scene and then visit again with the wearable camera. And after this system, together with my collaborators in Bristol, Andrew G. and Denis Chekhov and Andrew Calway, we developed many other SLAM systems that were far more robust than what you can see here. So this is 30 years ago, 20 years ago. But I think it's quite reasonable to ask the question of where is that XR, augmented reality or mixed reality assistant that works everywhere and that is always there with us helping. And I think we are still waiting for that. So what is the obstacle? Well, what is happening? So let me just go through what the traditional XR approach looks like. So one of the first steps that many of these systems first assume we need is that we have to have that world reference frame. So we have a camera that is worn by a person, maybe on a display, maybe on your shoulders, and you want to reference that camera relative to the world and a frame of reference. And then on top of that, you will want to put animations, augmentations. And this is not to put anyone on the spot. This is HoloLens. With my team, we have built very similar systems where you have
on top of
things like this. You have arrows, you have 3D annotations, you have 3D objects, and you expect the human to be able to follow these steps in order to complete a task. But what happens in reality is that things don't really work very well, and systems get stuck into things that we will discuss in a moment. But when things don't work very well, what we do is we blame the hardware or we blame the software. And I don't think this is really this is really going to get us anywhere from the point of view of having that elusive but very sought after XR assistant that helps you everywhere. So in my team for a few years now, we've been trying to motivate ourselves to try to address some of the big bottlenecks. And what are these bottlenecks that are still preventing us from having these assistive systems, these useful things? And in my opinion, it has never been the case that we needed sophisticated software or sophisticated hardware. Nowadays, we have these beautiful machines that are able to perform visual mapping on very small devices. And yet we're still missing these assistive systems. In my opinion, the things that are preventing us from taking that big next steps is things that are related to something that was identified 30 years ago, but we barely paid any attention. And let me go back to this slide, because what I'm talking about is this side of the problem. How to generate the content that you're going to display. The content generation was identified as a problem back in the days of the early Karma system, 30 years ago. But most of us, myself included, have spent quite a significant amount of time worrying about this other part, the part that had to do with positioning the camera and removing the requirements of having external devices. Like in this case, now we have everything on board. We can position the display relative to the world and so on. But we have ignored this other part. And this part, in my opinion, is what has always been a much bigger bottleneck, one that we really need to address in order to have these elusive XR systems helping us. So the authoring problem, how to create content, perhaps from hundreds of millions of users, brings this big problem of scalability. You could argue that many industrial systems, because everything is known, maybe you know the exact dimensions of the object and the steps and procedures that have to happen are very well controlled. You could argue that you don't have to worry about scalability because you can have one expert performing an operation and that's it. I'm much more worried about the things that ACVR is worried about, which is the common person and how to bring this to a lot of people and not just very well curated scenarios. So the scalability is a problem. And the other way that also limits the deployment of these things is also identifying when you want to deliver the content. So once you produce the content, when are you going to deliver it? So the content and the timing of the content are two big things. But perhaps the thing that costs us quite a lot of headaches is that we often forget that we have a person, a real human in the loop. And in some of the early systems and some of the very modern systems, we really make very, I will say, silly, myself and some of the systems that we have built do exactly this, very silly assumptions about the person requiring an indication in 3D space with an arrow, instead of just remembering that the person is perfectly capable of doing some of these structures without much extra information. So this is indeed motivated, as I mentioned, because daily living is full of circumstances where we just don't know what to do. We don't know how to fix a washing machine. We're not all technicians that will be able to understand what to do. This is meant to be an espresso machine. You might want to use it, but you really have no idea how well to use it. Or something that I have faced very recently, how to assemble my kid's bike. I spent about 5 hours trying to sort it out, and I just needed a little push that it never came from the instructions. So we face these problems pretty much every day. And the systems that we have around us don't really help us to address basic situations like this. But I argue that if we look back at what actually works with people, we will encounter this extremely powerful competence that we humans have, which is the power of imitation. So this is fundamental. This really is something that has allowed humans to evolve in many respects, because we have extremely rooted into the way in which our brain works, the ability of copying someone else. And this is explained by the motor mirror system. Some people argue if it really is there, but one thing that that is no denial is that we're able to see someone else making, let's say, fire in a better way than we actually can, and we can copy that person. And by the fact that we can copy that person, we learn and we are able to succeed in something that before we were not able to do as well or at all. And interestingly, this power of imitation is actually something that many other beings actually possess. And if you allow me, I will play this video, which is very interesting. This is a lizard watching the video of another lizard solving a problem. And because of that, then this lizard is able to achieve the goal. So I will play this. Let me know if
settles in to watch the movie where the hero dragon opens the gate. But will it help him solve the problem and get to the snack? An initial bout of headbanging suggests he's forgotten what he's seen in the video. But suddenly, Oscar makes a breakthrough, and he's gulping down his grubby reward. He's copied the dragon in the video almost perfectly, using his front foot to slide the gate to the left. For the 8 bearded dragons tested in this way, the results were the same. The dragons that didn't see the solution in the video couldn't do it, but the dragons that did were munching mealworms within seconds.
You get the idea, and what I'm trying to build towards is this other way, much simpler way that we might have ignored in the development of these much more sophisticated XR systems, which is that if we show the right video at the right time, people may be able to just perform the tasks that otherwise we assume we require sophisticated annotations and complex systems to support them. And this is indeed what with my collaborators we've been working towards. And the very first system that we put together with some of these ideas is one paper at BMC 2014, which is called You Do I Learn, that actually does quite a number of interesting things. So it gathers data from a lot of people. In this case, it actually had a visual slam system that was able to reconstruct parts of the world, and the system automatically, and this is the interesting thing, this automatic content authoring was happening even in this very early system, because the system was able to figure out where people were paying attention or interacting with things and extracting information in a way that the system knew what happened where. So I will play this video where it is essentially just illustrating how the system works. You Do I Learn from BMC 2014 looked at where people were looking at. So this actually had a gaze tracker and a camera, and the gaze tracker was informing the system where people were paying attention, and with the SLAM system we knew exactly where they were looking at in space. If there were moving objects, we were able to deal with them in other ways. But this is what the system was gearing towards. The system was gearing towards capturing small snippets of video of how people use the objects that you glance into. So if you see a screwdriver, what happens with a screwdriver? Well, one of the things that happens with a screwdriver is you plug it in. In the UK, there are these sockets where you have to turn it on before you plug something, so you're able to see what happens. So this system essentially allowed the gathering of the information that is happening around objects, and then displayed that information back to people in the way of small video guides. But we later took this even a step further, because what we wanted to do is to make a much more simpler system. And we wanted everything to be working in real time. The You Do I Learn was not working in real time. We were able to demonstrate we were capturing the relevant things and the relevant modes of interaction, but it was not fully integrated. So with the next system, following this principle of gathering video guidance at the right time and displaying it at the right moment, we developed a new system which is called Glacier, which is also fully automated. It's meant to work unsupervised, so there is no intervention about when the system is gathering what content, and is not also supervised in terms of or requesting from the person to actually ask for help. The system makes these decisions, and all works on board a extremely simple system, which is Google Glass, now discontinued for sure. But there were 3 basic components that we kept from the You Do I Learn and expanded. in Glacier, and the first one is the model of user's attention. Instead of having a gaze tracker, we had to invent something based on the head motion that I will explain in a moment. The system therefore decides when an expert is paying attention. So there's a teaching modality of the system, and it decides when the system is paying attention. It extracts after that relevant video snippets that we're then later going to play to a user. And then we connect everything with a object detector that all runs on board Glass. And so, as I said, Google Glass has no gaze tracker. So what we did is we actually train a system that, using the IMU, the inertial measurement unit from Glass, we were able to train it in a way that, based on the head motion, it approximated where the person was looking at. Especially this works well when you are in the vicinity of an object and you want to interact with that. The head motion almost stabilizes, and the angular velocity of the head reduces, so that you can detect actually when the person is actually operating something or doing something. And this seems to work fairly decently, because we can estimate with a good amount of time, let's say about 2 seconds before the person is about to interact with something, we can detect that. This is very good for when you teach the system. So we can start creating a video guide just before the person actually interacts with the right button or the right thing that they have to do. And then, as I mentioned, everything is glued together with an object detector. So this is, again, another paper that we published in BMC 2012, which is a method that is very fast, that runs on board Glass. So it's very lightweight. It's not using deep networks. So this is before that time, but it works really fast, especially for objects that have little texture. So essentially, when the system recognizes the object again, it can trigger the guidance, and this is how it works. So this is the system in action, where what we have here is a user that is interacting with a device. In this case, is just setting up an oscilloscope for the first time. The system observes this and captures one or multiple video guides, and this is essentially what the camera is seeing. So it's a small video guide of the basic steps that are happening in there. We do this for multiple people, so we have multiple experts teaching the system, and the system is essentially just detecting these moments of attention, gathering video snippets, and linking everything with the recognition of the object based on the appearance. We do this for multiple tasks. The system just gathers all this information, and then what happens afterwards is that there is this user that has self-declared, never set up or used an oscilloscope before, now observes what these guides that appear on the top of the visual field are, and is able to complete the task just by observing, in this case, a couple of times the video, without having to have any sophisticated spatial positioning or advanced computing. Just because the information that is required is provided at the right time, it's able to complete the task. So there's this paper of Glacier from Augmented Human in 2017 that explains in details. But essentially, we can show that the video guides that the system extracts are as good as the ones that the a curated ground truth expert is able to annotate. Okay, so I've been arguing about this important thing that is related to how we're going to gather the information in a scalable way, and gathering these video guides is very scalable compared to trying to produce 3D animations and 3D models for everything that exists in the world. Think about from cooking to assembling a mattress or fixing a bike. So imagine that you really want to do everything and have with you that superpower that allows you to feel that you can just do anything and operate any machine that is in front of you or do. But there is another very important thing that needs to be solved, and that is from all these huge amount of information that we can capture from all these video snippets that systems like Glacier or UDL Learn can capture, how can we decide who we're going to feature when someone requires help? So in my group with Hazel, Doty, and my colleague Dima Damen, we've been developing this notion that to me is very fundamental. Again, for trying to organize video collections, and it is how can we rank expertise, or how can we rank the skill of someone. And we have a CVPR 2018 paper that explains what we did. But imagine that you have tasks from drawing to surgery. How can we, from a collection of people and collection of videos of perhaps the same people, how can we organize that in a ranking fashion so that we can decide who are better and who are less good? This will be very important for a system that is automatically trying to gather information in order to decide what to show. And we have a follow-up paper in last year's CVPR where I will play a section of the video. Where we also do skill ranking, but in this case, there is attention modules that try to look for chunks in the video that help to rank towards what is good about the video, and chunks that help to rank what is bad about the video. So this is a more sophisticated system, and there is code for this in Hazel's webpage. Let me start again.
When assessing skill in long video, there may be variability in the skill exhibited throughout a video. In this example, the left video shows better skill in egg cracking. However, as the videos proceed, higher overall skill is shown in the right-hand video. Trained attention can also exclude parts irrelevant for skill assessment. Next, present qualitative results. We show video segments with strong attention responses for the low skill module from various tasks. In surgery, strain on the material is a sign of low skill present in only low-ranked videos. In apply eyeliner, segments show mistakes being fixed. In origami, the module attends to undoing previous folds. For high skill module attention responses, consistent performance can be seen in the segments, with straightening edges in dough rolling and origami. Interestingly, for drawing, pausing to consider is indicative of high skill. Next, we show videos ranked by our method and demonstrate the varying attention over time. Response of the high skill module, in green, show increased attention when a bean is being picked up. The low skill module, shown in red, attends to difficulties in gripping beans. In Tai Tai, we see that, for the most part, our method correctly ranks pairs of videos. It only struggles with pairs close in the ranking, such as the first and second videos displayed here. These are swapped in the ground truth. For longer tasks, such as scrambling eggs, filter responses are more sparse. Green demonstrates segments attended to by the high skill module, while red indicates the low skill module's attention weighting.
Okay, so this is along the lines of how to scale which is one of the main things that I was arguing. And there is much more to be done along these lines, but we are trying to address these bigger issues, which I argue before are like real bottlenecks for XR guidance, augmented reality, mixed reality systems. And along the lines of these, we have just released a new data set, which is called Epic Tent dataset, that is of a very complex object. Out of 29 participants, we asked them to pitch a tent, which is a very complex, flexible object. And there are many interesting things that happen when people do this for the first time. And have a look at this data set. Because you might encounter it as a challenge for conventional systems in computer vision, which is great. Okay, so in the first part of the talk, essentially, I argue towards being true and paying attention about things that work, and perhaps ignoring some of the things that may not work from the point of view of sophisticated hardware or assumptions about what people need or don't need when they need help. But there is also the case that not everyone, even if you have the guidance, you will be able to achieve physical or very precise motions that you require. So how can we help? How can we help in those circumstances? And this is another branch of work that in my group we've been exploring also for several years with, in this case, Yanis and Austin, that have been developing their PhDs in this space. And this space is what we call handheld robots. What is a handheld robot? Well, in robotics, we commonly have these two extrema. In one case, you have external robots, like robots that are meant to be totally independent. Perhaps you never see them because they're a vacuum cleaner that they work when you're not around, and so on. And in the other extreme, you have robots that are extremely close to you, like in the case of wearable or supernumerary robots that extend your physical capabilities, but some of these are even designed with the same dimensions that you have, so very, very tightly coupled with you. Handheld robots live in between these two extrema, and they look and behave at a general level like a handheld tool, but they have extra competences that are meant to support you to perform things. Primarily, handheld robots are meant to be intuitive to use. If you see a hammer, you have good ideas about how you can use that. And handheld robots are meant to also be intuitive to use in that way, are meant to also extend your capabilities without having to tightly integrate you to them, as in the case of supernumerary or wearable robots. But you maintain a strong sense of agency. You feel in control of the robot, and together with the robot, you are meant to be doing things. Handheld robots have existed in the past, but mostly in the field of medicine, trying to stabilize the hand of the surgeon, for example, when they are sculpting something or trying to cut something. But I believe that this concept of tools that are intelligent, that have context and understand the user, can be applied to many other fields, from maintenance to agriculture to cooperative applications in very extraneous circumstances, or daily living activities that allow you to do more than what you normally will be able to do with your physical capabilities. And so these handheld robots do have ways in which they sense the context, have task knowledge, so they know that the task is to drill, they know that the task is to do landscaping or things like that, and they get input from the user. in order to the user provides tactical motions, perhaps avoiding objects in between, but the robot can with all this information perform some controlled demands. And this video is one of the very first examples where we show how they work. Essentially, what you see here is a very basic handheld robot that has the task knowledge that you have to perform a pattern with these red and black tiles in there. And at some point, the robot senses that no more black tiles are required. And if you try to grab a black tile, the robot actually refuses and keeps pointing towards a red tile because that's what you need to do. So the robot is providing some cognitive and physical support to the user. And since then, we have been exploring other aspects, like, for example, how can the robot communicate with the person in order to better guide the person to where the robot needs to be. So in this case, we essentially compare 3 different ways in which the robot can communicate. We compare a virtual reality system, which is what you saw there. And we compare also without the robot, so just a normal handheld tool with all these 3 different ways to guide the person. So we compare virtual reality. We compared a 2D display, so super basic, so a 2D display. There is no stereoscopic view in this case, and also augmented reality. So we have a see-through display that this is what the person will be seeing through this augmented reality display. And because we also have the robot, we also have the ability of the robot just pointing to where it wants to go, and it's very intuitive. The robot starts pointing and you actually start following that, and the robot can achieve the goal, which is reached to a specific location. So we have tested multiple ways in which these robots can communicate with people. What do you think works better? It turns out that none of the display technologies has any statistical significance advantage over any of the other display technologies. So the fancy augmented reality display works as well as a 2D display. Why? Because in this case, you have the support of the robot. So the robot is able to position that tip in the accurate location, and it only needs some very basic tactical guidance. There is a small difference between the gesturing of the robot, so no display at all, and the other display technologies. So the display technologies do seem to help. But even without a display, the robot performs better than the handheld tool without the robot. So to me, what this is pointing out is, again, illuminating some aspects of what matters is that you provide the right information at the right time, and perhaps not so much important how you provide that information. And if you actually look at the ACVR topics of interest, one of them, which is of course a very big topic in robotics, is how can we predict what users want? And
excuse me, Walterio, sorry to interrupt. The quality of the screen is very low.
Thank you very much, Antonio, because I was on typing. Is
yeah,
it
that's
better
fine
now?
Yeah, it's
Thank you so much. Thank you. We have developed systems that allow the robot to predict what you want to do. Together with the task knowledge, that the robot knows what you want to do, and based on gaze tracking information and sensing of the world. In this case, in all our handheld robots, we use a motion capture system just for simplification. But the robot has all this information and predicts what you want to do. And this is another system. I will again switch to video mode, where let me stop and start again, because there is some audio that describes what's happening here. But in this case, the system predicts where you want to go, and it actually tries to frustrate you. I will explain this in a second, but let's listen to the video, please.
In this study, we explored gaze-based intention prediction for handheld robots. Here, the yellow line represents the user's gaze and object sizes indicate intention probabilities. The model was tested in 3 behavior modes. In the cooperative follow intention mode, the robot moves towards the predicted aim. In the rebel mode, the robot avoids the predicted aim and chooses a different available object instead. This sometimes led to situations where there was a mismatch between user and robot motion, so that users had to correct their plans. For a neutral reference, the robot moves to a random object in the third mode. We found that the robot is perceived more cooperative when it adapts its plans to users compared to imposing them.
So what's happening here is that the robot predicts where you want to go, but because it's extremely hard to measure the effect of a robot predicting your intentions is if you intervene in a situation like that, you essentially mess the experiment. What we thought is that it's much better that the robot frustrates you. So if it's much easier to measure frustration than to measure that the robot is cooperating with you. So essentially the robot, when it thinks that it knows what you want to do, it actually does the opposite of what you want to do. And then we measure frustration using other means. So this we found as a useful tool. And we have done other experiments where we also have remote users working together and mediated by the handheld robot, and we measure the ways in which they interact and communicate. And we can find interesting things like confirmation that the assistive mode is preferred by people versus the robot not helping you. But also we can measure that the communication, the number of commands that they have to exchange and the words they have to exchange reduces. And this robot is actually open source, so you can actually go and download from handheldrobotics.org, which is where we keep our models and our videos for this strand of work. And I know that we're about time, so I am finishing with this slide where I just want to bring together some of the things that we discussed, that in my opinion, these assistive augmenters are things that we have always strived to achieve. That's the story of technology overall. But when we are talking about these more advanced systems, scalability, predicting the user, and the balance of agency, who is in control and what exactly each one of these users is doing, are very significant things that we still need to overcome. And some things that are perhaps less often discussed, but is more important to talk about the what information and the when the information is delivered, and perhaps not worry too much about how we're going to deliver the information. So the sophisticated device may not be required to achieve a good deal of tasks. With this, I finish, and please let me know if there is chance for questions, but if not, please excuse me because I am in Seattle at the moment, and it's about 1 a.m. in the morning. I might not be able to stay around for the rest of the workshop, but I will be super happy to hear any questions by email if there is no time right now.